Light from this object takes over 10 billion years to reach us. When you look at TON 618, you're seeing something from when the universe was barely 3 billion years old. That single fact should tell you this isn't an ordinary black hole. We're going to explore the actual size of TON 618, and I need to be clear from the start. The numbers involved will challenge your ability to comprehend scale itself. This isn't hyperbole. The human brain didn't evolve to grasp distances measured in hundreds of billions of kilometers, or masses equivalent to 66 billion suns. But we're going to try anyway, using every comparison and perspective shift we can muster. By the end of this journey, you'll understand why TON 618 represents one of the most extreme objects physics allows to exist. You'll see why it shouldn't exist at all according to some theories, and you'll grasp why astronomers sometimes go quiet when they talk about it, as if they've stumbled onto something the universe forgot to keep hidden. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Let's start with where this monster lives. TON 618 sits near the border between two constellations you've probably never heard of, Canes Venatici and Coma Berenices. The distance is staggering in two different ways. The light we see left TON 618 roughly 10.8 billion years ago. That's the light travel time. But because the universe has been expanding while that light journeyed toward us, the actual co-moving distance is approximately 18.2 billion light years. Think about what that means for a moment. When the light currently hitting our telescopes began its journey, Earth didn't exist. Our sun didn't exist. The Milky Way looked completely different. Dinosaurs were still 4 billion years in the future, but distance is just the opening act. The real story is what TON 618 actually is. TON 618 is classified as a quasar, specifically a hyperluminous, broad absorption line, radio-loud quasar. That's a mouthful of technical terms that each reveal something crucial. Strip away the jargon and you're left with this. TON 618 is a supermassive black hole actively feeding on an enormous accretion disk of superheated matter, releasing more energy than most galaxies combined, while simultaneously blasting radio waves across the cosmos and driving powerful winds of material away from itself at thousands of kilometers per second. The black hole at the center is where things get genuinely uncomfortable for our sense of scale. Mass estimates vary depending on which measurement technique you trust. The higher estimate, widely cited in popular sources, puts TON 618 at 66 billion solar masses. That's 66 billion times the mass of our Sun. A more recent 2019 measurement using different spectral lines suggests 40.7 billion solar masses. Either way, we're talking about a black hole that contains more mass than all the stars in the entire Milky Way galaxy combined, which clock in at around 64 billion solar masses. Let that settle. This single object, this one black hole, has more mass packed into it than our entire galaxy's worth of stars. To put this in perspective, compare it to Sagittarius A star, the supermassive black hole at the center of our own Milky Way. Sagittarius A star weighs in at 4.3 million solar masses. It's not small by any standard. Its event horizon would fit inside Mercury's orbit. But TON 618 is roughly 15,300 times more massive. If Sagittarius A star is a marble, TON 618 is a beach ball the size of a house. Now let's talk about the physical size, because this is where your intuition completely fails. A black hole's size is defined by its Schwarzschild radius, the distance from the center to the event horizon, that point of no return where even light cannot escape. For TON 618, this radius measures approximately 1,300 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, roughly 150 million kilometers. So we're talking about 1,300 times that distance. The event horizon diameter, the full width across, is roughly 2,600 astronomical units, or about 390 billion kilometers. Let me give you a reference point that might help. Neptune, the most distant planet in our solar system, orbits the Sun at an average distance of 30 astronomical units. Pluto, out in the Kuiper Belt, averages about 40 astronomical units. The Kuiper Belt itself extends to roughly 50 astronomical units. TON 618's event horizon extends more than 40 times farther than Neptune's orbit. You could fit our entire solar system, from the Sun out to the Kuiper Belt, inside TON 618's event horizon more than 40 times over. Line up 40 complete solar systems side by side, and you just about span the diameter of this black hole's point of no return. Still having trouble visualizing it? Let's try this. Light travels at 299,792 kilometers per second. At that speed, light takes about 8 minutes to travel from the Sun to Earth. It takes light about 4 hours to reach Neptune. But to cross from one side of TON 618's event horizon to the other would take light, moving at the fastest speed possible in our universe, several weeks. NASA created a visualization comparing black holes, and when they reached TON 618 at the end, they noted that its shadow is so enormous that a beam of light would take weeks to traverse it. Compare that to M87, the famous black hole photographed by the Event Horizon Telescope. M87's black hole contains about 5.4 billion solar masses, and light would take roughly 2.5 days to cross its shadow. TON 618 is in a completely different category. The sheer scale creates a bizarre situation. If you could somehow observe TON 618 up close, which you absolutely could not survive, but let's pretend, the event horizon would look more like a wall or barrier stretching infinitely in all directions than a spherical boundary. Your human field of view couldn't encompass enough of it to perceive the curve. It would just be a flat black surface extending beyond your visual horizon in every direction, with space itself warping so severely near it that the laws of physics, as you understand them, would cease to make intuitive sense. Here's something that might disturb you. If you were falling toward TON 618, you could cross the event horizon without immediately noticing anything wrong. The gravitational gradient, the difference in gravitational pull between your head and feet, would be relatively gentle compared to smaller black holes. You'd pass the point of no return, still intact, still conscious, with no immediate sensation that anything had changed. Only later, as you continued falling, would tidal forces eventually tear you apart. But the crossing itself, almost peaceful. Smaller black holes rip you apart before you reach the event horizon. TON 618 is so large that its event horizon is almost gentle. Now let's consider what surrounds this monster, because TON 618 doesn't sit in empty space quietly existing. It's violently active. As a quasar, TON 618 is actively feeding. Matter spirals inward through an accretion disk, a swirling disk of gas and dust being pulled toward the event horizon. As this material accelerates and compresses, friction heats it to extreme temperatures. We're talking about millions of degrees in some regions. The accretion disk itself would extend for light days or even light weeks from the black hole. This superheated matter releases radiation across the entire electromagnetic spectrum: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. The amount of energy being released is almost incomprehensible. TON 618 shines with a luminosity of approximately 4 × 10 to the 40th power watts. To put that in more familiar terms, TON 618 is 140 trillion times brighter than our Sun. One object, outputting more light and energy than 140 trillion suns combined. The host galaxy surrounding TON 618, and there must be one because quasars sit at the centers of galaxies, is completely outshone by the central quasar. Despite potentially containing hundreds of billions of stars, the galaxy is invisible from Earth. The black hole's accretion disk is so bright that the entire galaxy is lost in the glare. Gas is falling into TON 618 at speeds approaching 7,000 kilometers per second. That's roughly 2.3% the speed of light. Material is being consumed at an enormous rate, converting mass to energy with terrifying efficiency. Some of this infalling gas has been measured, moving at speeds up to 10,500 kilometers per second, about 3.5% light speed, demonstrating the immense gravitational pull. But not everything falls in. TON 618 also drives powerful outflows. It's classified as a broad absorption line quasar, meaning its spectrum shows evidence of strong winds being driven away from the black hole. Radiation pressure from the accretion disk is so intense that it literally blows material outward at thousands of kilometers per second. These winds carry away significant amounts of matter and energy, potentially affecting star formation across the entire host galaxy. TON 618 is also radio loud, producing significant radio emissions from relativistic jets. These are streams of charged particles accelerated to near light speed, shooting outward perpendicular to the accretion disk. The jets carry enormous energy and extend far beyond the black hole itself, potentially reaching across hundreds of thousands of light years. In 2021, observations from the Atacama Large Millimeter Array revealed something remarkable: an enormous nebula of gas surrounding TON 618 and its host galaxy. This Lyman alpha blob, as it's called, has a diameter of at least 100 kiloparsecs, about 330,000 light-years. That's twice the diameter of our entire Milky Way galaxy. This nebula consists of 2 parts: an inner molecular outflow and an extensive cold molecular gas in the circumgalactic medium. Each part has a mass of approximately 50 billion solar masses. Combined, that's 100 billion solar masses of gas, more massive than the black hole itself. Both components are aligned with the radio jets, suggesting the black hole's activity has shaped the distribution of gas on truly galactic scales. This gas represents an enormous reservoir that could potentially fuel future star formation or be consumed by the black hole. The extreme radiation from TON 618 excites hydrogen in the nebula so intensely that it glows brightly in the Lyman alpha line, an ultraviolet wavelength. The nebula's existence and structure provide crucial insights into how galaxies formed in the early universe and how supermassive black holes influence their surroundings. The temperatures within TON 618's immediate environment reach approximately 38,000 degrees Celsius in some regions, with the innermost parts of the accretion disk potentially reaching millions of degrees. At these temperatures, atoms are completely ionized, and matter exists in a plasma state, emitting intense radiation. So that's the basic picture of TON 618, an ultramassive black hole, possibly the most massive ever directly measured, surrounded by a vast accretion disk releasing energy equivalent to 140 trillion suns, driving powerful jets and winds, embedded in a nebula twice the size of our galaxy, existing at a time when the universe was barely 3 billion years old. But understanding the scale, really grasping it, requires more than just numbers. In the next section, we're going to break down exactly what those numbers mean by comparing TON 618 to objects you can actually visualize. We'll work our way up from familiar scales to the truly cosmic, building a ladder of comprehension that might actually let you grasp what 66 billion solar masses really means. Because right now, even armed with all these facts, you probably can't truly picture it. That's what we need to fix. Let's start with something you understand. Yourself. You're about 1.7 meters tall, maybe a bit more or less. Hold that image. Now picture standing next to a blue whale, 30 meters long, the largest animal ever to exist on Earth. You'd barely reach its eye. That's a scale jump your brain can handle. Now take another leap. The International Space Station orbits 400 kilometers above Earth. You'd need to stack 235,000 blue whales end to end to reach it. That's starting to get difficult to visualize, but you can still sort of imagine it because you've seen pictures of Earth from space. The Moon sits 384,000 kilometers away, nearly 1,000 times farther than the ISS. Here's where most people's intuition breaks. The Sun is 150 million kilometers from Earth, 1 astronomical unit. That's the standard measuring stick for our solar system. Neptune, the outermost planet, orbits at 30 astronomical units. Pluto wanders out to about 40 astronomical units at its farthest point. The entire solar system you learned about in school, everything from Mercury to the Kuiper Belt, fits comfortably within 50 astronomical units. TON 618's event horizon has a radius of 1,300 astronomical units. Read that again. The edge of this black hole, not the accretion disk, not the surrounding nebula, just the point of no return where even light can't escape, extends 26 times farther than Pluto's orbit. If you place TON 618 where our Sun sits, its event horizon would swallow every planet, every asteroid, every comet, every piece of rock and ice in our entire solar system, and still extend outward into empty space for another 1,250 astronomical units. But that's just the event horizon. That's not even the full picture. Remember that accretion disk we discussed? The glowing maelstrom of superheated matter spiraling into the black hole. It would extend significantly farther, possibly light days or even light weeks from the event horizon itself. We're talking about a structure so vast that light, traveling at 300,000 kilometers per second, would take days to cross from one side to the other. Let's try another angle. Mass. Our Sun contains 99.86% of all the mass in our solar system. Jupiter, Saturn, All the other planets, the asteroid belt, everything, they're rounding errors compared to the Sun. The Sun is basically the solar system's mass budget. TON 618 contains 66 billion times more mass than that. The entire Milky Way galaxy, 200 billion to 400 billion stars, all the gas clouds, all the dust, all the planets orbiting all those stars, the supermassive black hole at our galactic center, everything has a total stellar mass of roughly 64 billion solar masses. TON 618, a single object, outmasses every star in our galaxy combined. Sagittarius A star, the black hole at the Milky Way's center, weighs 4.3 million solar masses. It's massive enough to hold our galaxy together, to orchestrate the orbits of billions of stars. TON 618 is 15,300 times more massive. When astronomers calculated these numbers, they had to double-check their math. The figures seemed wrong. They still seem wrong, even though we verified them through multiple independent methods. Here's what really breaks your brain. Light speed comparisons. You probably know that light from the Sun takes 8 minutes and 20 seconds to reach Earth. That's the light travel distance across one astronomical unit. Light from Neptune takes about 4 hours to reach us. The edge of our solar system? Light needs about 7 hours to get here from that far out. TON 618's event horizon is so enormous that a beam of light would take weeks to traverse its diameter. Not hours, weeks. The exact same light that crosses our entire solar system in 7 hours would need multiple weeks to travel across TON 618's shadow. Compare that to M87 star, the black hole we actually imaged with the Event Horizon Telescope in 2019. Humanity's first direct photograph of a black hole. That object made headlines worldwide. It weighs 5.4 billion solar masses, making it one of the largest black holes in the relatively nearby universe. Its shadow is so large that light takes about 2.5 days to cross it. TON 618 is more than 10 times larger. NASA created a visualization scaling up from small black holes to the largest known ones. The animation starts with black holes a few times the Sun's mass, then jumps to progressively larger objects. It works through dozens of intermediate black holes, steadily increasing in scale. M87 star appears near the end of this progression, dwarfing everything that came before it. The animation treats it as one of the final boss battles of cosmic scale. Then TON 618 appears, and M87 star looks small. Let's ground this in something tangible. Imagine you're an astronaut approaching TON 618. You're not falling in. You're just flying past at a safe distance, maybe a few light years away. You point your spacecraft toward it and start your approach at light speed. At that distance, TON 618 would appear as a point of light, brighter than anything in the sky, but still point-like. As you get closer, it starts to resolve. First, you'd see the accretion disk, a glowing spiral larger than any galaxy you've ever observed. The light isn't white. It's shifted across the spectrum from the intense gravitational effects. Space around the black hole is so severely warped that light from behind it bends around to the front, creating a halo effect. You'd see multiple distorted images of the accretion disks simultaneously, layered over each other in impossible geometry. You're still weeks away at light speed, weeks, and the structure keeps growing in your field of view. The accretion disk resolves into spiral arms, each one a river of plasma hot enough to vaporize anything that touches it. You'd see the jets, if you looked perpendicular to the disk. Columns of matter accelerated to 99.9% light speed, shooting outward for hundreds of thousands of light years. But the event horizon itself, you still couldn't see it directly. It's black, perfectly, absolutely black, because no light escapes it. You'd only see its silhouette against the accretion disk, a spherical absence where the universe simply stops. That absence would span thousands of astronomical units. Your entire solar system could fit in the gap between where the accretion disk's glow ends and where space itself becomes visible again on the other side. Now consider this from another perspective. TON 618 formed when the universe was only 3 billion years old. That's less than a quarter of the universe's current age. Somehow, in that cosmically brief period, this object accumulated 66 billion solar masses. That's not just impressive, it's theoretically problematic. Black holes grow by accreting matter. Material spirals inward, heats up, radiates energy, and eventually crosses the event horizon. But there's a natural speed limit to this process called the Eddington limit. When matter falls into a black hole, it releases enormous energy. That energy creates radiation pressure that pushes away additional infalling matter. The more massive the black hole, the higher its Eddington luminosity, but the relationship is linear. Double the mass, double the maximum accretion rate. For TON 618 to reach 66 billion solar masses in 3 billion years, it would need to accrete matter at rates that challenge or exceed the Eddington limit for significant periods. Standard astrophysical models struggle to explain how this happens. Either the early universe had conditions that allowed super Eddington accretion, or TON 618 formed from an unusually massive seed black hole, or it grew through an improbable series of mergers with other massive black holes. Possibly all three. Professor Andrew King from the University of Leicester calculated theoretical maximum masses for black holes in 2015. His work suggested that non-spinning black holes couldn't exceed 50 billion solar masses through accretion alone. The physics becomes self-limiting. Radiation pressure eventually prevents further growth. Spinning black holes can reach higher masses, potentially up to 270 billion solar masses, if they're rotating extremely fast. TON 618 sits at 66 billion solar masses. If it's not spinning rapidly, it's already exceeded theoretical predictions. If it is spinning rapidly, it might still have room to grow, but it's approaching the upper limits of what physics allows. We might be observing a black hole near the theoretical maximum size, a cosmic endpoint where growth becomes impossible. That surrounding nebula, remember? 330,000 light-years across, containing 100 billion solar masses of gas. That's not decorative. That's fuel. That's material that could potentially feed the black hole for millions or billions of years to come. But whether TON 618 can actually consume it depends on complex feedback mechanisms we don't fully understand. The black hole's radiation might heat and disperse the gas before it can fall in, or the gas might cool and collapse, providing sustained feeding. We're watching a cosmic drama whose ending we can't predict. Here's one more comparison that might help. Our sun will live for about 10 billion years total. It's currently halfway through that lifespan. When it dies, it'll puff off its outer layers and leave behind a white dwarf with about 60% of its current mass, roughly 0.6 solar masses. That white dwarf will then cool and fade for trillions of years. eventually becoming a black dwarf, a cold, dark cinder of carbon and oxygen. TON 618 could swallow 110 billion of those dead stars and still have room for more inside its event horizon. You can't actually picture this. Your brain isn't built for it. We evolved to understand scales from centimeters to kilometers, from seconds to decades. Our intuitions work for objects we can see and timescales we can experience. When you try to visualize 66 billion solar masses or structures spanning thousands of astronomical units, you're using mental tools designed for an entirely different problem set. But now you have the scaffolding. You understand the comparisons. You know that TON 618 outmasses our galaxy's stars combined, that its event horizon dwarfs our solar system, that light takes weeks to cross it, that it shouldn't exist according to some theoretical models, but does anyway. The numbers might not create a picture in your mind, but they create something else. Context for realizing just how far beyond normal cosmic scales this object sits. And there's another element to this scale problem that makes TON 618 even stranger than the numbers alone suggest. We've been talking about its mass, its size, its energy output, but we haven't talked about its age, or rather, when we're seeing it. The light reaching us from TON 618 has been traveling for 10.8 billion years. Think about what that means. When those photons left the vicinity of this monster, the universe was only 3 billion years old, barely a quarter of its current age. The sun didn't exist yet. Earth didn't exist. Our entire solar system wouldn't form for another 6 billion years. We're not observing TON 618 as it is now. We're observing it as it was in the cosmic equivalent of early childhood. And it was already this massive. That shouldn't be possible. Not according to our standard models of black hole formation and growth. Black holes grow primarily through two mechanisms: accreting matter from their surroundings or merging with other black holes. Both processes take time, a lot of time. Starting from stellar mass black holes, the kind formed when massive stars collapse, you'd need incredibly efficient growth over billions of years to reach even 1 billion solar masses. Reaching 66 billion solar masses in only 3 billion years requires something far more extreme. The Eddington limit becomes crucial here. It's the point where a black hole's radiation pressure from infalling matter exactly balances the gravitational pull bringing matter in. Push beyond this limit and the radiation should blow away the very material trying to fall into the black hole, choking off further growth. It's a self-regulating mechanism that prevents black holes from growing too quickly. But TON 618 somehow bypassed this. Either it grew through super Eddington accretion, somehow pulling in matter faster than the radiation pressure should allow, or it formed from an unusually massive seed, or it represents an improbable chain of mergers, or all three happened simultaneously. None of these explanations is particularly satisfying. Super Eddington accretion requires special conditions we don't fully understand. Massive seed black holes from direct collapse scenarios are theoretically possible, but observationally unconfirmed, and the merger scenario requires an unlikely confluence of events. Yet here sits TON 618, challenging our theories by simply existing. The discovery history adds another layer to this puzzle. TON 618 wasn't found yesterday with cutting-edge technology. It was photographed in 1957 at the Tonantzintla Observatory in Mexico during a survey of faint blue stars. On those photographic plates, it appeared decidedly violet, unusual enough to warrant catalogue's entry number 618. But quasars hadn't been recognized as a distinct class of objects yet. That wouldn't happen until 1963. So for 13 years, TON 618 sat in a catalogue as a mysterious violet dot, its true nature unknown. In 1970, a radio survey in Bologna detected radio emissions from its location, flagging it as potentially interesting. Marie-Helene Ulrich then obtained optical spectra at the McDonald Observatory, revealing emission lines characteristic of quasars. Only then did astronomers realize what they were looking at. Not a faint blue star in our galaxy, but a quasar billions of light-years away, powered by a black hole of incomprehensible mass. This delayed recognition isn't unusual in astronomy. We often observe things before we understand them, but it's particularly striking with TON 618 because of what the delay represents. Humanity's gradual realization that the universe contains objects operating at scales we hadn't imagined. The brightness makes TON 618 simultaneously visible and invisible. It shines with the luminosity of 140 trillion suns. With an absolute magnitude of -30.7, it's one of the brightest objects in the known universe. But that brilliance comes entirely from the accretion disk and surrounding material, not from stars in the host galaxy. In fact, we can't see the host galaxy at all. It's completely outshone by the central quasar, potentially hundreds of billions of stars, rendered invisible by the light from matter falling into the black hole. The galaxy exists, it has to, as galaxies host these supermassive black holes, but it's lost in the glare. That accretion disk deserves closer attention. Picture a structure extending light days or light weeks from the black hole, where matter spirals inward at velocities approaching 7,000 kilometers per second. That's over 2% the speed of light. The friction and compression heat this material to millions of degrees. At those temperatures, atoms are completely ionized. Electrons are stripped away, leaving bare nuclei colliding at relativistic speeds. The innermost regions reach the highest temperatures, potentially tens of millions of degrees near the event horizon, where orbital velocities peak. This superheated plasma radiates across the entire electromagnetic spectrum: radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays. Every wavelength tells us something about the physical conditions at different locations in the disk. The spectrum of TON 618 shows unusually wide emission lines. These lines come from gas in what's called the broad line region, located beyond the accretion disk, but still within the black hole's gravitational influence. The width of these lines indicates velocity. The faster the gas moves, the more the emission lines are Doppler shifted, creating broader features in the spectrum. Measurements show gas velocities reaching 10,500 kilometers per second in some regions. That's 3.5% the speed of light. This extreme velocity provides one of the key methods for estimating the black hole's mass. The faster gas must orbit to avoid falling in, the stronger the gravitational force, which directly relates to the central mass. Different research teams have used different spectral lines to estimate TON 618's mass, yielding different results. The original estimates using hydrogen beta emission lines suggested 66 billion solar masses. More recent measurements using carbon-4 emission lines produced a lower estimate, 40.7 billion solar masses. Both measurements use the same underlying data, but different calibration methods and assumptions. This uncertainty matters. If TON 618 is only 40 billion solar masses, it's still extraordinarily massive, but falls within some theoretical predictions. At 66 billion solar masses, it exceeds certain theoretical limits for non-spinning black holes, making it even more problematic for standard models. The truth probably lies somewhere in that range, but the uncertainty reflects fundamental challenges in measuring black hole masses at such extreme distances. We're not weighing these objects directly. We're inferring their masses from the motion of surrounding gas, which requires assumptions about the geometry, viewing angle, and dynamical state of the system. Beyond the accretion disk and broad-line region lies something even more remarkable. The Lyman Alpha Nebula, discovered through observations with the Atacama Large Millimeter Array in 2021. This structure spans at least 330,000 light-years, twice the diameter of the Milky Way. It consists of two distinct components: an inner molecular outflow, likely driven by winds from the accretion disk and jets from near the black hole, and an extensive region of cold molecular gas in the circumgalactic medium, the diffuse halo of material surrounding the galaxy. Each component contains roughly 50 billion solar masses of gas. Combined, that's 100 billion solar masses, more than the black hole itself. This nebula isn't just decoration. It's evidence of the black hole's influence extending across galactic scales. The intense ultraviolet radiation from the quasar ionizes hydrogen in the nebula, causing it to emit the Lyman alpha line, a specific ultraviolet wavelength. This emission is so strong that TON 618 is classified as a Lyman alpha blob, one of the largest such objects known. The alignment of the nebula with the radio jets suggests a physical connection. Jets are narrow beams of charged particles accelerated to near light speed, shooting outward perpendicular to the accretion disk. For TON 618, these jets carry enormous energy and momentum, potentially shaping how gas is distributed across hundreds of thousands of light years. This interaction between the black hole and its environment represents feedback. The black hole affects its surroundings, which in turn affects how much matter can fall back into the black hole. Strong feedback can regulate or even halt black hole growth by heating and dispersing the gas that would otherwise feed it. Whether TON 618 is currently in a feedback-limited state or still growing actively remains unclear. The surrounding nebula contains enough material to fuel continued growth for millions or billions of years. But whether that material can actually reach the black hole depends on complex processes we don't fully understand. TON 618 is also classified as radio-loud, meaning it produces substantial radio emissions beyond what comes from the accretion disk alone. This radio emission originates from the jets, where magnetic fields accelerate electrons to relativistic speeds. As these electrons spiral around magnetic field lines, they emit synchrotron radiation, predominantly in radio wavelengths, but extending into other parts of the spectrum. The jets themselves are poorly understood. We know they exist because we detect their radiation. We know they carry substantial energy because the radio emission is so strong. But the exact mechanism that launches them remains debated. It involves the black hole's spin, magnetic fields threading the accretion disk, and the extraction of rotational energy from the black hole itself through a process called the Blanford-Zanajek mechanism. For TON 618, The jets are aligned with the nebula structure, suggesting they've been active long enough to shape their environment significantly. These outflows can suppress star formation by heating gas and preventing it from collapsing into stars. They can also trigger star formation in some regions by compressing gas clouds. The net effect depends on local conditions and the jet's power. TON 618 also shows broad absorption lines in its spectrum, another classification tag. These absorption features indicate high-velocity winds flowing outward from the quasar, likely driven by radiation pressure. These winds can reach thousands of kilometers per second, carrying away substantial amounts of matter and energy. This outflow represents yet another feedback mechanism. As the black hole accretes matter and releases energy, some of that energy drives winds that expel material, potentially limiting how much can fall in. Over cosmic time, this feedback may be why supermassive black holes and their host galaxies show correlated properties. The black hole's growth and the galaxy's evolution are intimately linked through these feedback processes. Studying TON 618 in detail presents significant observational challenges. Its extreme distance makes it appear faint despite its intrinsic brightness. The redshift stretches all wavelengths. Ultraviolet light is shifted into the visible range, visible light into infrared, and so on. This complicates observations, but also provides opportunities, as the redshift moves some spectral features that would normally be blocked by Earth's atmosphere into observable wavelengths. The host galaxy remains invisible, outshone by the quasar. Current technology can't separate the galaxy's starlight from the overwhelming glare of the central engine. Future telescopes, like the James Webb Space Telescope or planned extremely large telescopes, may eventually resolve details about the host galaxy's stellar population, mass, and structure. What we do know is that TON 618 represents a crucial window into the early universe. Quasars were much more common when the universe was young, during an era of rapid galaxy formation and black hole growth. As the universe aged and expanded, galaxies consumed or dispersed much of their gas, reducing fuel availability. Quasar activity declined as a result. Modern galaxies typically have quiet supermassive black holes, accreting slowly if at all. Our own Sagittarius A star is relatively inactive, consuming matter at a modest rate. But in TON 618's era, conditions favored active growth. Galaxies were forming and merging frequently. Gas was abundant. Black holes grew rapidly, powering brilliant quasars visible across the cosmos. TON 618 catches this process near its peak, showing us what the universe looked like during this transformative period. The fact that such massive black holes existed so early constrains models of cosmic evolution. It tells us about initial conditions in the universe, about how matter was distributed, about how quickly structures formed. It tells us about the physics of black hole formation in conditions vastly different from today's universe. But here's something that doesn't quite add up. TON 618 shouldn't exist, at least not according to some of our models. The universe was only 3 billion years old when TON 618 looked the way we see it now. That's barely enough time for galaxies to form, let alone for a black hole to accumulate 40 to 66 billion solar masses. Standard accretion theory predicts growth rates that simply can't produce something this massive this quickly. The math doesn't work. Think about it this way. Black holes grow by consuming matter. But there's a natural speed limit to this process called the Eddington limit. When matter falls toward a black hole, it heats up and releases radiation. That radiation pushes outward. At some point, the outward radiation pressure equals the inward gravitational pull. The system reaches equilibrium. Matter can't fall in faster than the radiation can escape. This sets a maximum growth rate. Even starting from a stellar mass black hole, say 100 solar masses, and accreting at the Eddington limit continuously for 3 billion years, you'd only reach a few billion solar masses, not 40 billion, not 66 billion. The timeline doesn't allow it. So how did TON 618 get so big so fast? Several theories attempt to explain this puzzle. One possibility involves direct collapse. Instead of forming from a stellar remnant, perhaps some primordial black holes formed when massive gas clouds in the early universe collapsed directly, bypassing the stellar phase entirely. These seeds would start much heavier, maybe 10,000 or even 100,000 solar masses. That gives them a head start. Another idea suggests super Eddington accretion. Maybe under the right conditions, black holes can temporarily exceed the Eddington limit. The early universe was dense with gas. Perhaps TON 618 found itself in an environment so rich with fuel that it gorged itself, growing faster than the standard limits predict. Some simulations show this might work if the accretion disk is geometrically thick and radiation escapes preferentially in certain directions rather than pushing uniformly outward. There's also the merger scenario. If multiple black holes formed early and merged repeatedly, they could build mass more quickly than accretion alone allows. Each merger adds the combined mass instantly, without needing to wait for gas to spiral in. A series of such mergers, combined with steady accretion between events, might produce an ultramassive black hole within the available time. None of these explanations is entirely satisfying. Each has problems. Direct collapse requires very specific conditions that may not have been common. Super Eddington accretion faces theoretical challenges about stability and radiation escape. Mergers require an improbably high rate of collisions early on. Yet TON 618 exists. The universe doesn't care about our theoretical difficulties. This brings us to another fascinating aspect of TON 618. It might be approaching its maximum possible mass. In 2015, astrophysicist Andrew King calculated theoretical mass limits for black holes based on accretion physics. He found that for a non-spinning black hole, the maximum mass achievable through accretion is roughly 50 billion solar masses. If the black hole spins rapidly in the same direction as its accretion disk, this limit increases, potentially to 270 billion solar masses. The reason involves the innermost stable circular orbit. As a black hole gains mass, this orbit moves outward. Eventually, it reaches a point where the gravitational pull at the ISCO isn't strong enough to hold gas together against its own self-gravity. The disk becomes unstable and can't deliver matter to the black hole efficiently. Growth stalls. TON 618, with mass estimates ranging from 40.7 to 66 billion solar masses, sits right at or above King's limit for non-spinning black holes. If the higher mass estimate is correct, TON 618 might already be near its accretion-based growth ceiling. It could be one of the most massive black holes physically possible through this mechanism. But black holes can still grow through mergers. When two black holes orbit each other and eventually collide, they combine their masses. This process doesn't face the same radiation pressure constraints as accretion. So even if TON 618 has maxed out its accretion potential, it could continue growing by consuming other black holes. Of course, there's competition for the title of largest black hole. Phoenix A, another ultramassive black hole, has been cited with mass estimates around 100 billion solar masses. However, that measurement carries significant uncertainty. Different techniques and assumptions produce different results. The black hole at the center of the Phoenix cluster is enormous, but pinning down its exact mass remains challenging. Another contender is the black hole in the quasar SDSSJ 140821.67 plus 0 25733.2. Try saying that 3 times fast. Its mass estimates also reach extreme values, though again with substantial uncertainty. The competition for largest black hole depends heavily on measurement techniques and which data sets you trust. Recently, in 2025, astronomers discovered what they're calling the cosmic horseshoe black hole, weighing in at 36 billion solar masses. This discovery used a combination of gravitational lensing and stellar kinematics, a technique that provides more direct mass measurements than spectroscopic methods alone. The cosmic horseshoe ranks among the top 10 most massive black holes known, possibly top 5. But even at 36 billion solar masses, it's still smaller than TON 618's estimates. The difficulties in precisely measuring black hole masses mean rankings can shift. New techniques emerge. Old measurements get revised. What's clear is that TON 618 remains a top contender, consistently appearing in discussions of the universe's most massive black holes. What about its size? Not its mass, but its physical dimensions. The event horizon of a black hole scales with its mass. For TON 618, the Schwarzschild radius, the distance from the center to the event horizon, is approximately 1,300 astronomical units. Remember, 1 AU is the distance from Earth to the Sun, about 150 million kilometers. TON 618's event horizon extends 1,300 times that distance. To put it another way, the event horizon's diameter is roughly 2,600 astronomical units. Neptune orbits the Sun at about 30 astronomical units. TON 618 could swallow our entire solar system, out past Neptune, past the Kuiper Belt, more than 40 times over. Its event horizon is larger than the orbits of all our planets combined, with room to spare. NASA created a visualization comparing black hole sizes. It starts with stellar mass black holes, moves through Sagittarius A star at the Milky Way's center, continues to M87's black hole, the one famously imaged by the Event Horizon Telescope, and ends with TON 618. M87's black hole has an updated mass of 5.4 billion solar masses. Its shadow is so large that a beam of light traveling at 300,000 kilometers per second would take about 2.5 days to cross it. TON 618's shadow dwarfs even that. Light would take weeks to traverse it. Weeks. Think about what that means. Light circles Earth's equator more than 7 times in 1 second. Yet it would need weeks to cross TON 618's shadow. The scale defies comprehension. This shadow, the apparent size of the event horizon as seen by a distant observer, is actually larger than the Schwarzschild radius due to gravitational lensing. The intense gravity bends light around the black hole, creating an optical illusion that makes the shadow appear bigger. For TON 618, this effect amplifies an already incomprehensible size into something even more extreme. Standing on a planet orbiting TON 618, if such a planet could exist, you'd see a region of absolute blackness dominating the sky. Not just a dark spot. A void so vast it would cover a significant fraction of the visible sky, surrounded by a ring of tortured, red-shifted light from the accretion disk wrapping around the event horizon's curve. Of course, you couldn't actually stand there. The tidal forces would tear you apart long before you got close. The radiation would cook you. The environment is utterly hostile to any conceivable form of life. But as a thought experiment, it illustrates the sheer presence such an object would have. Inside the event horizon, causality breaks down. All paths lead inward. You can no more avoid falling toward the singularity than you can avoid moving forward in time. The singularity itself, the point of infinite density at the black hole's core, remains hidden from view, shielded by the event horizon. We can't observe it directly. General relativity predicts its existence, but also suggests our equations break down there, requiring a theory of quantum gravity we don't yet have. TON 618's temperature profile offers another window into its extremes. The accretion disk's emissions reveal temperatures around 38,000 degrees Celsius. That's the temperature of gas in the outer regions of the disk, already hot enough to ionize atoms and produce intense ultraviolet radiation. Closer to the black hole, temperatures climb even higher, millions of degrees. At those temperatures, matter exists in a plasma state. Electrons are stripped from atoms. The gas emits X-rays and gamma rays. This temperature gradient drives the luminosity. Hotter regions emit more energy. The inner disk, where temperatures peak, produces the most intense radiation. As matter spirals inward, it releases gravitational potential energy. For TON 618, this process converts mass to energy with extraordinary efficiency, far better than nuclear fusion. That's why quasars shine so brilliantly despite their compact size. The alignment of TON 618's radio jets with its nebula suggests a long period of sustained activity. Jets don't form instantly. They require stable accretion and a strong magnetic field maintained over time. The fact that the nebula structure mirrors the jet orientation indicates these outflows have been shaping their environment for millions, possibly tens of millions of years. TON 618 isn't a brief flare. It's a persistent, powerful engine that has been running for a significant fraction of cosmic history. This persistence raises interesting questions about duty cycles. Quasars don't stay active forever. Fuel supplies run low. Feedback mechanisms shut down accretion. The quasar phase ends, leaving behind a dormant, supermassive black hole. How long does TON 618 have left? Is it near the end of its active phase, or just getting started? We can't say for certain, but given its enormous mass and the vast reservoir of gas in the surrounding nebula, TON 618 likely has fuel for continued activity for some time yet. When TON 618 eventually runs out of easily accessible fuel, it will fade. The accretion disk will thin. The jets will weaken and shut off. The brilliant quasar will dim, revealing the host galaxy that currently remains hidden beneath the glare. At that point, TON 618 will resemble the quiet, supermassive black holes we see in modern galaxies, massive but dormant, waiting for a fresh supply of gas to reignite. That future state represents the endpoint of quasar evolution. All modern galaxies with supermassive black holes likely went through quasar phases in their youth. Sagittarius A star at the Milky Way's center probably shone as a quasar billions of years ago. Now it's quiet, accreting slowly, producing only faint emissions. TON 618 shows us what our galaxy's core might have looked like in its prime, a blazing beacon visible across the universe. This evolutionary trajectory connects TON 618 to every massive galaxy we observe today. The correlation between black hole mass and galactic properties isn't coincidental. Supermassive black holes and their host galaxies grow together through a process called coevolution. When a quasar blazes at full power, its radiation and jets heat surrounding gas, preventing it from cooling and forming stars. This feedback mechanism regulates both star formation and black hole growth. Without it, galaxies would convert gas into stars too quickly, exhausting their fuel supply and looking nothing like the galaxies we observe. TON 618 exemplifies this process in action. Its powerful jets inject energy into the surrounding medium. The Lyman Alpha Nebula shows clear signs of this interaction. Gas heated and ionized by radiation, structures aligned with jet directions, velocities consistent with outflows. The black hole isn't just consuming gas, it's reshaping its entire environment, determining what gas cools and forms stars, what gas gets heated and dispersed, what structures emerge from the cosmic raw materials. This feedback operates on multiple scales simultaneously. Close to the black hole, within the accretion disk, temperatures reach millions of degrees. Radiation pressure becomes so intense, it can reverse the inflow, creating winds that blow material away. Farther out, jets deposit energy across hundreds of thousands of light years. Even farther, at megaparsec scales, the cumulative effect of many quasars heats the intergalactic medium, affecting cosmic structure formation itself. The efficiency of this process depends critically on the Eddington limit, the balance point between gravity pulling matter inward and radiation pressure pushing it outward. For a black hole of TON 618's mass, the Eddington luminosity is enormous, roughly 10 to the power of 40 watts. TON 618 shines at approximately 4 times that value, suggesting super Eddington accretion. How does it manage this? Several mechanisms might enable super Eddington rates. If the accretion disk is geometrically thick rather than thin, radiation can escape along the poles, while matter continues flowing in along the equator. If the accretion flow is clumpy rather than smooth, dense clumps can shield material behind them from radiation pressure. If the black hole is spinning rapidly, frame-dragging effects near the event horizon can extract rotational energy, supplementing the luminosity without requiring more accretion. TON 618's spin remains unknown. Measuring black hole spin requires observing features near the event horizon, the innermost stable circular orbit, relativistic line profiles, or spin-dependent efficiency of accretion. For an object 10.8 billion light-years away, these measurements exceed current capabilities. We can only infer spin indirectly from luminosity and accretion signatures. But spin matters enormously for maximum mass. Andrew King's theoretical work showed that a non-spinning black hole growing through accretion should max out around 50 billion solar masses. Beyond that mass, the innermost stable circular orbit moves outward past the point where gas self-gravity can hold it together. The accretion disk fragments, growth stalls. However, a rapidly spinning black hole aligned with its accretion disk can reach masses up to 270 billion solar masses before hitting this limit. TON 618's mass, whether 40.7 billion or 66 billion solar masses depending on the measurement, places it near or potentially above the non-spinning limit. If the higher mass estimate is correct, TON 618 must be spinning significantly. If the lower estimate holds, it might be approaching its maximum size regardless of spin. Either way, TON 618 likely won't grow much larger through accretion alone. Mergers offer an alternative growth path. When two black holes orbit each other, they lose energy to gravitational waves and eventually merge. The resulting black hole has mass equal to the sum of the original masses minus the energy radiated as gravitational waves, typically a few percent. For supermassive black holes like those in TON 618's mass range, mergers could add tens of billions of solar masses in a single event. The early universe, when TON 618 was active, experienced higher galaxy merger rates than today. Galaxies were closer together. Dark matter halos were still assembling. Major mergers happened frequently. Each merger brought gas to fuel the quasar and potentially delivered another supermassive black hole to merge with the central one. This environment favored rapid black hole growth through both accretion and mergers. But mergers also pose challenges. When two supermassive black holes enter the same galaxy, they don't immediately merge. They must first sink to the galactic center through dynamical friction, interactions with stars and gas that extract energy and angular momentum. This process works well initially, but slows as the black holes form a bound binary. Getting from a wide binary separation down to merger requires additional mechanisms. Interactions with a third black hole, a dense stellar cusp, or a circumbinary gas disk. This final parsec problem has puzzled theorists for decades. Some massive black hole binaries might stall at separations of about a parsec, never merging on timescales shorter than the age of the universe. If true, this would limit how quickly black holes can grow through mergers. However, recent simulations suggest that in gas-rich early universe conditions, circumbinary disks provide sufficient torque to drive mergers. TON 618 might have grown partly through such mergers. The broad absorption line features in TON 618's spectrum hint at powerful outflows. These absorption lines appear blue-shifted to shorter wavelengths, indicating material moving toward us at high velocities. The gas absorbs specific wavelengths from the quasar's light, creating dark lines in the spectrum. The width and velocity of these lines reveal outflow speeds reaching thousands of kilometers per second. These outflows aren't accretion disk winds alone. They're large-scale galactic winds driven by radiation pressure and jets. Gas accelerated to these velocities carries enormous kinetic energy, enough to heat the surrounding medium and potentially expel it from the galaxy entirely. This represents the feedback mechanism in its most direct form. The black hole literally blowing away its own fuel supply. The mass outflow rate can be estimated from the absorption line properties. For TON 618, outflows likely carry away hundreds to thousands of solar masses per year. Compare this to the accretion rate needed to power the quasar, several hundred solar masses per year based on luminosity. The outflow and accretion rates are comparable. For every bit of matter the black hole consumes, roughly an equal amount gets expelled. This balance determines the system's evolution. If outflows exceed accretion too much, the quasar starves and shuts down. If accretion dominates, the black hole grows without limit. The fact that we observe TON 618 in a roughly balanced state suggests self-regulation. The quasar adjusts its own fuel supply through feedback, maintaining conditions where it can shine brightly without either exhausting its gas reservoir too quickly or growing uncontrollably. The radio-loud classification indicates significant jet power. Only about 10% of quasars produce powerful radio jets. The distinction correlates with black hole spin and magnetic field configuration. Jets require strong magnetic fields threading the accretion disk and event horizon. As the black hole spins, it drags these fields around, extracting rotational energy and launching plasma along the spin axis at relativistic speeds. TON 618's jets punch through the accretion disk and continue outward, eventually creating radio lobes millions of light years across. These lobes aren't visible in current observations due to TON 618's distance, but they must exist based on the radio spectrum. The jets deposit energy in the intergalactic medium, heating it and potentially triggering or suppressing star formation in smaller galaxies they encounter. Jet speeds approach the speed of light. Particles accelerated to such velocities produce synchrotron radiation, emission from charged particles spiraling in magnetic fields. This produces the radio signature we detect. The total power in the jets can be estimated from radio luminosity, typically a few percent of the quasar's total luminosity. For TON 618, jet power might reach 10 to the power of 39 watts or more, enough to power a trillion suns worth of energy output in mechanical form. The alignment between jets and the Lyman Alpha Nebula structure suggests these outflows have been stable for millions of years. Jets can be intermittent, turning on and off as accretion rates vary. But producing the observed nebula structure requires sustained jet activity. The gas didn't just get blown away randomly, it was shaped and sculpted by persistent, directed outflows. This stability implies a stable accretion geometry. The accretion disk maintains its orientation over long periods. The black hole's spin axis stays aligned with the disk. Major disturbances, like galaxy mergers or sudden gas infall from unusual directions, would disrupt this alignment and potentially shut down the jets temporarily. The fact that we see stable jets suggests TON 618 has had a relatively undisturbed recent history, at least on timescales of millions of years. The nebula's mass, 100 billion solar masses total, exceeds the black hole's mass significantly. This gas represents the building material for future stars or future black hole accretion. If conditions allow, the nebula could form thousands of massive star clusters over the next few billion years. Alternatively, if the quasar remains active, it might gradually consume much of this material. The fate depends on cooling times. Hot gas must cool before it can collapse and form stars. Cooling depends on density and temperature. In the inner regions, where the quasar's radiation keeps the gas ionized and hot, cooling times exceed the age of the universe. This gas won't form stars anytime soon. In outer regions, where radiation is weaker, cooling times shorten. Star formation might proceed there, building the stellar halo of the host galaxy. This process mirrors what we see in modern galaxies. Massive elliptical galaxies contain old stellar populations with little ongoing star formation. Their gas is hot and diffuse, kept that way by past quasar activity and ongoing heating from old stars. The quasar phase ended billions of years ago, but its effects persist. TON 618 shows us this process in progress, the moment when a quasar is actively suppressing star formation through feedback. The Lyman alpha emission itself provides a diagnostic tool. This ultraviolet line occurs when electrons in hydrogen atoms transition from the first excited state to the ground state. The photon energy corresponds to 10.2 electron volts, placing it in the UV. TON 618's extreme luminosity produces copious UV radiation that ionizes the surrounding hydrogen. When electrons recombine, they cascade down through energy levels, producing Lyman alpha photons. The nebula glows brightly in this line because the quasar provides the energy source. Turn off the quasar, and the nebula would fade on timescales of thousands to millions of years, the time needed for electrons to recombine and for Lyman alpha photons to scatter out of the nebula. The current brightness tells us the quasar has been active recently, within the past few million years at most. Scattering matters here. Lyman alpha photons don't escape directly. They scatter off neutral hydrogen many times before finally escaping. This resonant scattering can trap photons for extended periods, creating a diffuse glow around the source. The nebula's extended structure partially results from this scattering process. Photons produced near the quasar random walk outward through scattering, eventually emerging at large distances. The velocity structure of the nebula encodes its history. Different regions show different velocities relative to the quasar. Some gas moves toward us, some away, some orbits the black hole. By mapping these velocities using spectroscopy, astronomers reconstruct the three-dimensional structure and dynamics. The ALMA observations that revealed the molecular gas component provided precisely this information. Velocity maps showing how gas flows through the system. These observations showed two distinct components. The inner molecular outflow moves at hundreds of kilometers per second, directly driven by the quasar's jets and radiation. The extensive circumgalactic medium moves more slowly, representing gas that's been affected by the quasar but not directly expelled. Both components contain molecular hydrogen, H2, rather than just atomic hydrogen. This indicates sufficient density and shielding for molecules to survive, despite the intense radiation environment. Molecular gas is star formation fuel. Under the right conditions, it collapses to form stars. The presence of 100 billion solar masses of molecular gas around TON 618 suggests enormous star formation potential. Yet current observations show the gas remains mostly diffuse. Why isn't it forming stars now? Turbulence provides one answer. Gas must be relatively calm to collapse under its own gravity. Turbulence, random motions on various scales, provides support against collapse, similar to thermal pressure. The jets and outflows from TON 618 inject turbulent energy, stirring the gas and preventing collapse. Only once the quasar shuts down and turbulence dissipates can star formation proceed efficiently. Temperature offers another factor. Molecular gas must cool to about 10 Kelvin to form stars. Warmer gas has too much thermal pressure. The quasar's radiation heats the gas directly through photoionization and indirectly through UV photons that dissociate molecules and free atoms that then recombine, releasing heat. This heating maintains temperatures too high for star formation. Magnetic fields, add additional complexity. Molecular gas contains embedded magnetic fields that provide extra support against gravitational collapse. Field strengths and geometries remain poorly constrained for TON 618, but analogy with other systems suggests fields play a significant role. Turbulence can amplify fields through dynamo action. Strong fields resist compression, further suppressing star formation. All these factors combine to keep TON 618's nebula in a state of suspended potential, vast amounts of gas capable of forming stars, but prevented from doing so by the quasar's ongoing activity. This state won't last forever. Eventually, the gas supply runs low, accretion slows, the quasar dims, and conditions shift. Then the nebula can cool, fragment, and form the next generation of stars that will comprise the mature galaxy. This suspended state represents a pivotal moment in cosmic history. We're witnessing the transition between violent quasar-driven activity and the mature galaxy that will emerge afterward. Other systems at lower redshifts show us snapshots of later stages in this process. Quasars dimming, gas cooling, star formation igniting. TON 618 catches the system at peak activity, maximum energy input, before the inevitable decline begins. How long does this phase last? Quasars don't shine forever. Their lifetimes depend on fuel supply and feeding efficiency. For systems like TON 618, typical quasar lifetimes range from tens to hundreds of millions of years. Brief by cosmic standards, but long enough to profoundly reshape their environments. The current bright phase might persist for another 50 million years before fuel depletion forces the black hole into dormancy. What signals the transition from active to dormant? The accretion rate provides the key metric. As long as sufficient gas reaches the black hole, the quasar continues shining. Once the supply diminishes, whether through consumption, expulsion, or changes in the galactic environment, the accretion rate drops. The disk cools, the jets weaken, the radiation field dims. This happens gradually over millions of years, not suddenly. During this transition, the nebula's fate becomes sealed. Without the quasar's energy input, turbulence dissipates, heating stops, magnetic fields decay. The gas begins cooling through radiation, losing energy to space. Molecular hydrogen excels at cooling. Its rotation and vibration states efficiently radiate away thermal energy. Over several tens of millions of years, temperatures drop from hundreds of Kelvin to the critical 10 Kelvin threshold, where gravitational collapse becomes inevitable. Once cooling proceeds sufficiently, fragmentation begins. The once uniform nebula breaks into clumps. Each clump contracts under its own gravity. As contraction continues, densities rise, triggering further collapse. Eventually, these fragments become dense enough and hot enough at their cores to ignite nuclear fusion. Stars are born. The process transforms the diffuse nebula into a stellar population, converting 100 billion solar masses of gas into perhaps 10 to 20 billion stars. This star formation won't happen uniformly throughout the nebula. Different regions will form stars at different times and rates. The densest regions collapse first. The most turbulent regions resist collapse longest. Regions with stronger magnetic fields form stars more slowly. The result is a complex, extended period of star formation, lasting hundreds of millions of years. What kind of galaxy emerges from this process? The answer depends on many factors: the nebula's angular momentum, its density distribution, the history of mergers with other galaxies. The massive black hole at the center suggests a massive elliptical galaxy forms eventually. Ellipticals contain old stellar populations, little gas, and limited ongoing star formation, consistent with a system that consumed or expelled most of its gas during an earlier active phase. The host galaxy likely already contains some older stars formed before TON 618 became a quasar. These stars are invisible to us now, outshone by the quasar's brilliance. But they exist, orbiting the black hole, contributing to the galaxy's total mass. The nebula will add to this existing population, creating multiple generations of stars with different ages and compositions. Can we see examples of this process at later stages? Yes. Astronomers study post-starburst galaxies, systems that recently ceased forming stars after an intense burst. These objects show strong absorption lines from massive stars that formed within the past billion years, but lack the emission lines indicating ongoing star formation. They represent what TON 618's host might look like a few billion years from now. We also study massive elliptical galaxies in the nearby universe, the descendants of systems like TON 618. These contain ancient stellar populations, dormant supermassive black holes, and little gas. Their stars orbit in random directions rather than in organized disks, suggesting formation through violent processes involving mergers and feedback. The Milky Way's neighbor M87 provides an example, a massive elliptical with a 5.4 billion solar mass black hole, now quiet after its quasar phase ended long ago. TON 618's nebula encodes the galaxy's future in its present structure. The total gas mass determines the final stellar mass. The velocity structure determines the galaxy's rotation. The density distribution determines where stars form. Reading this information requires detailed observations that push current instruments to their limits. The alignment between the nebula and the radio jets reveals something crucial about the system's geometry. Jets emerge perpendicular to the accretion disk, following the black hole's spin axis. The fact that the molecular outflow and circumgalactic medium both align with this axis indicates the jets have shaped the gas distribution on scales from thousands to hundreds of thousands of light years. This shaping happens through momentum transfer. Jets carry enormous kinetic energy. When they collide with surrounding gas, they transfer momentum, pushing gas outward and sideways. The collision creates shocks, abrupt increases in pressure and temperature, that heat and compress the gas. These shocks drive the molecular outflow, launching gas at hundreds of kilometers per second away from the galaxy's center. But jets do more than push gas around. They also inject energy throughout the nebula. High-energy particles streaming along the jets interact with surrounding matter through collisions and electromagnetic interactions. This heats the gas and generates radiation across the spectrum. The process, called jet-driven heating, helps maintain the nebula's elevated temperature and prevents premature star formation. Magnetic fields play a critical but poorly understood role. The jets themselves contain strong magnetic fields. Field lines wound up by the rotating accretion disk and carried outward by flowing plasma. These fields extend into the nebula, threading through the gas. Field pressure provides additional support against gravitational collapse. Field tension can accelerate gas perpendicular to field lines. Understanding the magnetic field structure remains a major observational challenge. Different regions of the nebula likely have different magnetic field strengths and geometries. Near the jets, fields are strong and well organized, aligned with the jet direction. Farther out, fields weaken and become more tangled due to turbulence. In the densest clumps, fields may be compressed and amplified. This complexity makes modeling the system extremely difficult. The circumgalactic medium represents the nebula's outer envelope, gas extending to hundreds of kiloparsecs, but not directly expelled by jets or winds. This gas has a different origin than the inner outflow. It might be primordial material that never fell into the galaxy. It might be gas expelled by earlier feedback episodes. It might be material tidally stripped from smaller galaxies, merging with the host. Its presence indicates a complex history of gas flows into and out of the galaxy. This outer gas reservoir serves another function beyond future star formation. It regulates the system's evolution. As the quasar expels gas from the inner regions, this outer reservoir can flow back inward, potentially reigniting accretion and restarting the quasar. This creates a feedback cycle where active and dormant phases alternate over hundreds of millions of years. Whether TON 618 has experienced previous cycles remains unknown. The mass budget provides important constraints. The black hole contains 40 to 66 billion solar masses, depending on the measurement. The nebula contains 100 billion solar masses of gas. The existing stellar population likely contains several hundred billion solar masses, though we can't observe it directly. The total baryonic mass in the system exceeds 500 billion solar masses, comparable to the most massive galaxies in today's universe. Dark matter dominates the total mass. The galaxy sits within a dark matter halo, containing perhaps several trillion solar masses. This dark matter provides the gravitational potential well that holds the system together. Without it, the violent feedback from the quasar would have dispersed the nebula entirely. Dark matter's gravity keeps everything bound, despite the intense radiation pressure. The interplay between baryonic matter and dark matter shapes the galaxy's structure. Baryons cool and concentrate toward the center, where they form stars and feed the black hole. Dark matter remains distributed more broadly in a roughly spherical halo. The ratio between baryonic and dark matter mass in the central regions exceeds the cosmic average because baryons have concentrated through dissipative processes while dark matter cannot. Chemical composition adds another layer of complexity. The gas in TON 618's nebula isn't pure hydrogen and helium. It contains metals, elements heavier than helium produced by stellar nucleosynthesis. These metals, though comprising only a small fraction by mass, profoundly affect the gas's behavior. They enhance cooling through emission lines. They provide opacity, affecting radiation transfer. They eventually become incorporated into planets and life. Where do these metals come from? Stars that formed earlier in the host galaxy or in smaller galaxies that merged with it. These stars lived their lives, fused lighter elements into heavier ones, and expelled material through stellar winds or supernova explosions. That enriched material mixed with primordial gas, raising the metallicity. The current metallicity in TON 618's nebula likely reaches 20 to 50% of the solar value. Not pristine, but not fully enriched either. This intermediate metallicity tells us about the galaxy's history. It formed stars before becoming a quasar. Those stars produce the metals we now observe. But the majority of star formation hasn't happened yet. That awaits the nebula's collapse after the quasar shuts down. The final stellar population will have higher metallicity than the current nebula because ongoing star formation will continue enriching the gas. The spatial distribution of metals within the nebula likely isn't uniform. Regions closer to the black hole experienced more intense radiation and heating, possibly affecting chemical processes. Regions where jets interact with gas might show different compositions due to shock chemistry. Mapping metallicity variations requires spectroscopic observations at multiple positions, observations that challenge current instrumental capabilities. Dust adds further complications. A small fraction of metals condenses into solid grains, dust particles typically smaller than a micron. These grains affect radiation transfer by absorbing and scattering light. They also catalyze molecule formation by providing surfaces where atoms can meet and bond. The amount and distribution of dust in TON 618's nebula remain poorly constrained, but certainly affect the system's evolution. Observing dust directly requires infrared observations. Dust absorbs ultraviolet and optical light from the quasar, heats up, and re-radiates in the infrared. The resulting infrared emission provides information about dust mass, temperature, and distribution. For TON 618, such observations require space-based infrared telescopes. Ground-based instruments can't access the relevant wavelengths due to atmospheric absorption. Future observations will revolutionize our understanding. The James Webb Space Telescope's infrared capabilities can probe the dusty regions around TON 618. The extremely large telescope, once operational, will provide unprecedented spatial resolution in optical and infrared light. Next-generation radio arrays will map molecular gas with exquisite detail. These facilities will transform TON 618 from a distant curiosity into a detailed laboratory for studying galaxy evolution. What questions remain unanswered? Many. We don't know the precise three-dimensional geometry of the nebula. Current observations provide projections on the sky, but not depth information. We don't know the detailed velocity field throughout the entire structure. We don't know how magnetic fields vary spatially. We don't know the metallicity distribution. We don't know the dust content. We don't know whether the host galaxy has experienced previous active phases. Answering these questions requires coordinated observing campaigns using multiple telescopes across the electromagnetic spectrum. Radio observations map molecular gas. Infrared observations probe dust and obscured star formation. Optical observations trace ionized gas. X-ray observations reveal the hottest material near the black hole. Each wavelength provides complementary information about different components and processes. The challenge lies in combining these diverse observations into a coherent physical model. Different observations sample different physical conditions, temperatures, densities, ionization states. Connecting them requires detailed modeling of radiative transfer, chemistry, and dynamics. Computational simulations help by predicting what observations should show for different model parameters, allowing comparison between theory and observation. TON 618 represents more than an individual object. It's a window into cosmic dawn, showing us galaxy formation in action. By studying it and similar systems at high redshift, we reconstruct the processes that built today's galaxies. We learn how black holes and galaxies co-evolve. We understand how feedback regulates star formation. We trace the chemical enrichment of the universe. Each distant quasar adds another piece to this cosmic puzzle. The broader implications extend beyond individual systems. TON 618's existence constrains theoretical models of the early universe. How common were such massive black holes? Current surveys suggest ultramassive black holes are rare but not unique. Several candidates exist with comparable masses. Their scarcity indicates special conditions were needed for their formation. Perhaps they required unusually dense environments where gas could collapse rapidly. Perhaps they formed from direct collapse scenarios rather than stellar remnants. Perhaps they grew through exceptionally efficient accretion or rapid merger sequences. Population studies matter here. By cataloging all known ultramassive black holes and analyzing their properties statistically, astronomers can infer the conditions that produce them. Do they preferentially appear in certain cosmic environments? Do they show correlations with particular galaxy types? Do their host galaxies share common characteristics? These questions guide searches for additional examples and inform simulations of early structure formation. The theoretical framework faces genuine challenges. Standard accretion models predict growth timescales. A stellar mass black hole of 10 solar masses accreting at the Eddington limit would require hundreds of millions of years to reach 1 million solar masses. Reaching 40 billion solar masses within 3 billion years, the time available given TON 618's redshift, pushes these models to their limits. Super Eddington accretion provides one solution. If black holes temporarily exceeded the Eddington limit during particularly gas-rich phases, they could grow faster than conventional models allow. Another possibility involves massive seed black holes. Instead of starting from stellar remnants of tens of solar masses, perhaps some black holes began with thousands or even millions of solar masses. Direct collapse scenarios propose that under certain conditions, massive gas clouds could collapse directly into black holes without forming stars first. These scenarios require specific circumstances, pristine gas lacking metals that would enable cooling and fragmentation, intense radiation fields preventing normal star formation, rapid infall preventing feedback from disrupting the collapse. Whether such conditions existed in the early universe remains debated. Merger-driven growth offers yet another pathway. If multiple smaller black holes merged repeatedly in dense galactic environments, the combined mass could grow rapidly. Each merger would release gravitational waves and potentially kick the remnant black hole through recoil. But in sufficiently massive dark matter halos, the black hole would remain gravitationally bound and continue growing through subsequent mergers and accretion. Numerical simulations explore these scenarios, calculating expected growth rates and comparing them to observations. The physics near TON 618's event horizon defies everyday intuition. At 1,300 astronomical units, the Schwarzschild radius exceeds the size of our entire solar system 40 times over. Light itself would take weeks to cross from one side to the other. A beam of light traveling at 300,000 kilometers per second, traversing a distance so vast that our planetary system becomes insignificant by comparison. Matter approaching this boundary experiences gravitational forces strong enough to tear apart stars long before crossing the event horizon. Tidal forces scale inversely with black hole mass for equal distances from the center. Paradoxically, This means crossing the event horizon of an ultramassive black hole like TON 618 would be less violent than crossing into a stellar mass black hole. The tidal gradient, the difference in gravitational force across an object's extent, decreases for larger black holes. An astronaut falling into TON 618 could theoretically cross the event horizon without immediate spaghettification. The fatal tidal forces would manifest closer to the singularity, deep within the event horizon's interior. This counterintuitive result highlights general relativity's subtleties. The event horizon isn't a physical surface. Nothing marks its location locally. An infalling observer would notice nothing special upon crossing. No wall, no barrier, no sudden change. Only later, attempting to escape, would they discover the impossibility of their situation. All future-directed paths lead inward. No amount of thrust could reverse course. The event horizon represents a one-way membrane in space-time itself. Hawking radiation introduces quantum effects. Even black holes emit thermal radiation due to quantum fluctuations near the event horizon. The temperature depends inversely on mass. Stellar mass black holes have temperatures of millionths of a Kelvin. TON 618's temperature would be proportionally lower, trillionths of a Kelvin, far colder than the cosmic microwave background. Such black holes gain mass from background radiation faster than they lose mass to Hawking radiation. They grow rather than evaporate. Only in the distant future, after stars cease forming and the universe cools below even the minuscule Hawking temperature, would ultramassive black holes begin evaporating. The timescale for complete evaporation scales as the cube of the mass. For TON 618, this exceeds 10 to the 100th power years, a number so large it dwarfs the current age of the universe by unimaginable factors. The black hole would outlast not just stars, but the very concept of conventional time in any recognizable sense. The information paradox lurks here. What happens to information that falls into a black hole? Does it disappear, violating quantum mechanics' unitarity principle? Does it somehow escape through Hawking radiation? Does it remain encoded on the event horizon? These questions remain unresolved, despite decades of theoretical work. TON 618, like all black holes, embodies this fundamental tension between general relativity and quantum mechanics. String theory and other quantum gravity approaches propose solutions. Perhaps black holes aren't truly black, but rather fuzzballs, quantum objects without event horizons. Perhaps the interior connects to other universes through wormhole-like structures. Perhaps information is preserved through holographic principles where the event horizon's surface encodes the volume's information. None of these ideas have achieved consensus, and experimental tests remain far beyond current capabilities. Gravitational waves from TON 618's formation and growth might carry information. When black holes merge, they produce gravitational waves, ripples in space-time itself, propagating at light speed. Detectors like LIGO and Virgo observe mergers as stellar mass black holes. Future space-based detectors like LISA will access lower frequencies corresponding to supermassive black hole mergers. Detecting gravitational waves from ultramassive black hole mergers would require even more ambitious instruments, but the scientific payoff would be enormous. Such detections would reveal black hole spins, masses, and orbital parameters with precision impossible through electromagnetic observations. They would test general relativity in the strong field regime, where space-time curvature reaches extreme values. They would provide independent mass measurements to compare with spectroscopic estimates. They would probe the merger history of massive galaxies across cosmic time. The challenge lies in the timescales. Gravitational wave signals from ultramassive black holes have periods of days to years. Detecting them requires continuous monitoring over extended periods, correlating data from multiple spacecraft to achieve sufficient sensitivity. The signals would be weak. Even the most massive mergers produce only tiny strains in spacetime by the time waves reach us. But the scientific returns justify the technological investment. TON 618's jets deserve closer examination. Radio observations reveal powerful outflows carrying enormous energy into the surrounding medium. The jet launching mechanism involves complex magnetohydrodynamics near the event horizon. Magnetic fields threading the accretion disk become twisted and amplified by differential rotation. The fields extract rotational energy from the black hole itself through the Blandford-Znajek process, channeling it into collimated outflows traveling at near-light speeds. These relativistic jets interact with ambient gas, creating shock waves and turbulence. They inflate enormous radio-emitting bubbles visible in low-frequency observations. They deposit energy across vast regions, heating gas and preventing it from cooling and forming stars. This feedback mechanism helps explain why the most massive galaxies today contain relatively little cold gas, despite their enormous masses. Their central black holes expelled or heated the gas during previous active phases. For TON 618, the jets align with the Lyman Alpha Nebula's major axis. This alignment isn't coincidental. The jets shape gas distribution by pushing material perpendicular to their propagation direction. Gas swept into the jet's path gets accelerated, heated, or dispersed. Gas lying perpendicular to the jets experiences less direct interaction, allowing it to accumulate into the observed nebula structures. The jet power must be substantial, perhaps 10 to the power of 46 ergs per second, equivalent to the luminosity of 1 trillion suns. Magnetic fields throughout the system remain poorly constrained. Theory predicts strong fields near the black hole where they drive jets. Fields in the accretion disk channel plasma and affect angular momentum transport. Fields in the nebula might influence gas dynamics and star formation. But observing these fields directly proves difficult. Polarization measurements provide indirect evidence, showing that radiation has interacted with magnetic fields. Future radiopolarimetry could map field structures in detail. The host galaxy's stellar population remains essentially invisible, overwhelmed by the quasar's brilliance. Estimates suggest it likely contains hundreds of billions of stars based on the black hole galaxy mass relationship observed in nearby systems. This relationship, the M-sigma relation, correlates black hole mass with the velocity dispersion of stars in the galactic bulge. Extrapolating to TON 618 suggests a galaxy mass exceeding 1 trillion solar masses. Such a galaxy would rank among the most massive ever formed. Its dark matter halo would be correspondingly enormous, perhaps containing 10 trillion solar masses or more. The halo provides the gravitational well within which gas accumulates. Galaxies merge and structure grows. Understanding the halo's properties requires gravitational lensing observations. If a background galaxy fortuitously aligns with TON 618, its light would be bent and magnified, revealing the foreground mass distribution. Such alignments are rare, but not impossible. The cosmic web context matters. Large-scale structure simulations show that the most massive halos form at the intersections of filaments, the nodes where cosmic structure is densest. TON 618 likely occupies such a node, positioned where multiple filaments meet. Gas flowing along filaments converges at these locations, providing abundant fuel for black hole growth and star formation. The system's environment probably included numerous companion galaxies, some of which may have merged with the host over time. Simulations help interpret observations by predicting what structures should look like under different assumptions. Cosmological simulations follow the evolution of dark matter from early density fluctuations to present-day structures. Adding gas physics, star formation, and black hole feedback allows comparison with observed galaxies. The simulations that best match observations constrain physical processes and parameter values, refining our understanding of how galaxies form. TON 618 provides a particularly stringent test. Its extreme properties, ultramassive black hole, enormous nebula, powerful jets, must all emerge naturally from physical processes operating in the early universe. Simulations that produce TON 618-like systems reveal which conditions and mechanisms were necessary. They guide observers toward key measurements that would distinguish between competing models. They suggest what future telescopes should look for when studying similar high redshift quasars. Future telescopes will transform our understanding. The James Webb Space Telescope, already operational, can detect infrared light from TON 618's host galaxy, piercing through dust that obscures optical observations. Webb's sensitivity allows imaging of structures near the quasar that were previously invisible, potentially revealing star formation regions, galactic morphology, and companion objects. The extremely large telescope, scheduled for completion in the late 2020s, will provide unprecedented angular resolution from the ground. Its 39-meter mirror will resolve features 10 times smaller than current telescopes can achieve, possibly distinguishing different regions within TON 618's accretion disk, or detecting individual star clusters in the host galaxy. Square-kilometer array radio observations will map the jets and magnetic fields with exquisite detail. This instrument's collecting area, equivalent to a square kilometer of radio antennas, will detect faint emissions from outflows and trace gas dynamics throughout the system. Combined with ALMA's molecular line observations, SKA data will reveal how jets shape the circumgalactic medium and regulate star formation across hundreds of thousands of light years. X-ray observatories like Athena, planned for the 2030s, will probe the high-energy physics near TON 618's event horizon. X-rays trace the hottest gas in the accretion disk's inner regions, where temperatures reach millions of degrees. Spectroscopy of these X-rays reveals chemical abundances, ionization states, and velocities, constraining accretion physics and testing general relativity in extreme gravitational fields. Time-resolved X-ray observations could detect variability caused by orbiting hotspots or magnetic reconnection events. Gravitational wave detectors might eventually sense TON 618's influence. Current detectors like LIGO and Virgo aren't sensitive enough to detect gravitational waves from individual supermassive black holes, but future space-based detectors, concepts like LISA, we'll observe lower frequency waves produced by merging supermassive black holes. If TON 618's black hole formed through mergers, as some theories suggest, similar events occurring today would generate detectable signals. These observations would reveal black hole spins, masses, and merger histories directly. Multi-messenger astronomy combines electromagnetic observations with gravitational waves and neutrinos. If TON 618's jets accelerate particles to ultra-high energies, neutrino detectors might register signals from nuclear interactions in the jet plasma. Neutrinos travel unimpeded through space, arriving simultaneously with photons from the same event despite traversing different paths. Detecting neutrinos from TON 618 would confirm hadronic acceleration mechanisms and constrain jet composition. Statistical studies of similar objects provide context. TON 618 isn't unique. It's the most massive example of a population. Surveys identifying hundreds of high redshift quasars enable statistical analyses of their properties, clustering and evolution, the distribution of black hole masses, accretion rates, and host galaxy properties reveals patterns that individual objects can't show. Comparing TON 618 to its peers highlights what makes it exceptional and what characteristics are typical for ultramassive systems. Quasar luminosity functions track the number density of quasars at different luminosities and redshifts. These functions show that luminous quasars were more common in the early universe, peaking around redshift 2 to 3 when the universe was 2 to 3 billion years old. TON 618, at redshift 2.2, formed during this peak epoch. The decline in quasar activity at later times suggests that black hole growth rates decreased as gas supplies dwindled and feedback mechanisms became more effective at regulating accretion. Clustering analyses measure how quasars are distributed in space relative to the large-scale structure. Quasars occupy the most massive dark matter halos, clustered in overdense regions where galaxy formation is most active. TON 618's position within the cosmic web determines its environment and influences its evolution. If located at a filament intersection, it would have access to copious gas supplies flowing along multiple filaments. If isolated in a massive halo, its fuel supply would depend more on internal processes like galaxy mergers. Chemical evolution studies trace element abundances through cosmic history. Early generation stars produced light elements, carbon, oxygen, nitrogen. Later generations synthesized heavier elements, iron, silicon, magnesium. The spectrum of TON 618's broad-line region shows strong emission lines from carbon, nitrogen, and oxygen, indicating that significant stellar nucleosynthesis had already occurred by the time the quasar formed. The gas fueling the black hole had been enriched by previous generations of stars, constraining the timeline of star formation in the host galaxy. Metallicity measurements quantify these abundances relative to hydrogen. Solar metallicity refers to the chemical composition of our Sun. About 2% of its mass consists of elements heavier than helium. Measurements of TON 618's broad-line region suggest metallicities approaching or exceeding solar values, implying substantial prior star formation. This enrichment occurred within the first billion years of the galaxy's existence, requiring rapid star formation rates and efficient mixing of stellar ejecta throughout the interstellar medium. Dust observations provide additional constraints. Dust grains form when heavy elements condense in the cool outflows from dying stars. Infrared observations detect thermal emission from dust heated by starlight or quasar radiation. The infrared luminosity indicates the dust mass and temperature, revealing the star formation history and the balance between dust production and destruction. For TON 618, infrared observations show substantial dust, consistent with vigorous star formation, either currently ongoing or in the recent past. Star formation rates in the host galaxy remain uncertain due to contamination from quasar light. Typical estimates for luminous quasars at similar redshifts suggest rates of hundreds to thousands of solar masses per year. If TON 618's host galaxy forms stars at this pace, it would build a stellar mass exceeding 1 trillion solar masses within 1 billion years, consistent with the implied galaxy mass from the black hole galaxy correlation. Such rapid star formation requires enormous gas reservoirs and efficient conversion of gas into stars. Stellar initial mass function affects predictions. This function describes the relative numbers of stars formed at different masses. A standard IMF produces mostly low-mass stars with fewer massive stars. Alternative IMFs with more massive stars would yield different chemical enrichment patterns, luminosities, and feedback effects. Observations of stellar populations in distant galaxies suggest that the IMF may vary with redshift or environment, complicating interpretations of star formation rates and chemical evolution. Supernova feedback influences both star formation and black hole growth. Massive stars explode as supernovae after only a few million years, injecting energy and momentum into surrounding gas. This feedback heats and disperses gas, potentially suppressing subsequent star formation. In dense environments, supernovae might trigger star formation by compressing nearby gas clouds. The balance between suppression and triggering determines the overall star formation efficiency and the timescale over which galaxies build their stellar populations. Active galactic nucleus feedback operates on larger scales. Radiation pressure, jets, and winds driven by the central black hole affect the entire galaxy and its circumgalactic medium. This feedback can quench star formation by heating or expelling gas, explaining why the most massive galaxies observed today have relatively low star formation rates despite their large gas reservoirs. TON 618's powerful feedback likely regulates star formation in its host, potentially transitioning the galaxy from an active star-forming phase to a quiescent, passive phase. Observations of other massive galaxies suggest this transition occurred in the past several billion years. Massive elliptical galaxies in the nearby universe contain old stellar populations with little ongoing star formation. These galaxies likely experienced intense starburst phases at high redshift, then quenched due to AGN feedback or exhaustion of gas supplies. TON 618 may represent an earlier stage in this evolutionary sequence, captured during the peak of both black hole growth and star formation before feedback mechanisms shut down both processes. Merger histories affect structure. Hierarchical structure formation predicts that massive galaxies assembled through numerous mergers of smaller galaxies. Each merger brings gas that can fuel starbursts and black hole accretion. The stellar populations formed during different merger events have distinct ages and metallicities, creating complex distributions that observations can potentially disentangle. TON 618's host likely experienced multiple major mergers, each contributing to its current mass and triggering episodes of quasar activity. Dynamical modeling reconstructs these histories, Simulations that reproduce observed properties reveal plausible formation pathways. For TON 618, models must explain how the black hole grew so massive so quickly while simultaneously building the host galaxy's stellar population. Successful models typically invoke either continuous rapid accretion from dense gas streams or episodic bursts of accretion triggered by mergers. Both scenarios require specific initial conditions and environmental factors that may be rare, explaining why ultramassive black holes like TON 618 are uncommon. Observational biases affect discovery rates. Luminous quasars are easier to detect than faint ones, so surveys naturally find the brightest examples like TON 618. Fainter quasars with smaller black holes might outnumber the ultramassive ones, but remain undetected due to instrumental sensitivity limits. Correcting for these biases requires careful statistical analysis of survey selection functions, allowing astronomers to infer the true number density of black holes at different masses. Variability studies track changes over time. Quasars vary in brightness due to fluctuations in accretion rate or changes in obscuration. Monitoring TON 618 over months or years could reveal variability patterns that constrain the accretion disk's size and structure. Shorter timescale variations probe smaller spatial regions closer to the black hole, while longer-term trends reflect changes in the overall fuel supply or feedback processes. Spectroscopic monitoring detects changes in emission line profiles. If the broadline region's structure evolves, line widths and intensities shift accordingly. Reverberation mapping exploits these changes to measure the region's size by timing the delay between continuum variations and line response. For TON 618, such measurements would refine black hole mass estimates and test whether the broadline region's properties differ from those in less extreme systems. Polarization measurements reveal magnetic field geometries and scattering processes. Light from the accretion disk becomes polarized through scattering off electrons or alignment of dust grains by magnetic fields. The degree and direction of polarization encode information about field strength, orientation, and the distribution of scattering material. For TON 618, polarization data would constrain jet magnetic fields and accretion disk structure, complementing spectroscopic and photometric observations. The broader cosmological context matters. TON 618 formed during an epoch when the universe's structure was rapidly evolving. The cosmic star formation rate peaked around redshift 2, then declined as gas was consumed and feedback mechanisms became more efficient. Understanding why this transition occurred requires studying objects like TON 618 that exemplify the peak phase. Their properties constrain models of gas accretion, star formation, and feedback that govern galaxy evolution. Dark energy's influence becomes relevant on the largest scales. The accelerated expansion of the universe affects structure growth by counteracting gravitational collapse. In the distant future, dark energy will prevent new structures from forming and eventually tear apart gravitationally bound systems. But during TON 618's epoch, dark energy's effects were minimal, allowing structures to grow rapidly through gravitational instability. The current dominance of dark energy marks a transition point in cosmic history, after which structure formation slows dramatically. TON 618 offers a window into processes that shaped the universe. Its extreme properties, ultramassive black hole, intense luminosity, enormous nebula, powerful jets, reflect conditions in the early universe that no longer prevail. Studying this system reveals how galaxies formed from primordial gas, how black holes grew to dominate galactic centers, and how feedback regulated the transformation from actively star-forming systems to passive ellipticals. Every observation adds another piece to this cosmic puzzle. The system's fate remains uncertain over cosmic timescales. Will the black hole continue growing through mergers, eventually exceeding theoretical mass limits? Will feedback mechanisms shut down accretion permanently, leaving a quiescent remnant? Will the host galaxy merge with neighbors, triggering new episodes of activity? These questions await answers that observations over coming decades will provide. What we know today represents a beginning. TON 618 challenges our understanding and pushes theoretical models to their limits. It exemplifies the universe's capacity for extremes, objects so massive, so luminous, so energetic, that they redefine what we consider possible. In studying this cosmic giant, we confront fundamental questions about growth, limits, and the processes that govern the largest structures in existence. The numbers don't lie, but they don't quite capture it either. You now know that TON 618's event horizon spans 2,600 astronomical units. You understand that light takes weeks to cross its shadow. You've grasped that it outmasses every star in our galaxy combined. But knowing these facts and truly comprehending them remain different things entirely. Your brain isn't wired for this scale. Evolution shaped your intuitions for objects measured in meters, distances covered in hours, masses you can lift or at least imagine lifting. TON 618 exists so far outside this comfortable range that even armed with precise measurements and careful comparisons, you can't really picture it. The best you can do is understand the relationships, how it compares to things slightly less incomprehensible, building a ladder of analogies that points toward but never quite reaches the truth. What makes TON 618 genuinely remarkable isn't just its size. Plenty of things in the universe are large. Galaxy clusters span millions of light years. Cosmic voids stretch across hundreds of millions. The observable universe itself measures 93 billion light years across. Size alone doesn't make something special. The remarkable aspect is concentration. 66 billion solar masses packed into a region you could traverse at light speed in a few weeks. That concentration creates gravitational fields so intense they warp space-time into shapes that break your intuitive understanding. It creates energy densities that shouldn't exist according to some theoretical limits. It produces feedback effects that reshape entire galaxies across hundreds of thousands of light years. TON 618 represents physics operating at the edge of what's possible. Black holes can't grow arbitrarily large through accretion. Radiation pressure eventually prevents further growth. Theoretical calculations put this limit around 50 billion solar masses for non-spinning black holes, potentially higher for rapidly spinning ones. TON 618 sits right at this boundary, possibly already at its maximum accretion-based mass. It's not just big, it's as big as a black hole can get through the standard growth mechanism. The timeline makes it worse. This object assembled its mass within 3 billion years of the Big Bang. Standard growth models struggle to explain this. You can't simply start with a stellar mass black hole and grow it to 66 billion solar masses in that time frame using conventional accretion. The math doesn't work. Something unusual happened. Either the seed black hole started much more massive than stellar remnants typically provide, or accretion proceeded faster than theoretical limits suggest, or multiple massive black holes merged in rapid succession, or all three occurred simultaneously. We don't know which explanation is correct. Each has problems. Direct collapse scenarios require special conditions that may not have been common. Super Eddington accretion faces stability issues. Rapid merger sequences seem statistically unlikely, yet TON 618 exists anyway, indifferent to our theoretical difficulties. The surrounding nebula adds another layer to this puzzle. 100 billion solar masses of gas extending 330,000 light-years, twice the Milky Way's diameter. This isn't just decoration, it's fuel. It's the raw material for future star formation or continued black hole growth. The nebula's structure, aligned with the radio jets, shows how the black hole has already shaped its environment on galactic scales. Radiation and outflows have redistributed gas, heated it, ionized it, preventing it from cooling and collapsing into stars. This feedback mechanism explains why massive galaxies today contain relatively little cold gas despite their enormous masses. Their central black holes expelled or heated most of it during earlier active phases. TON 618 shows us this process in action. The moment when a quasar is actively regulating its own fuel supply and suppressing star formation throughout its host galaxy. Eventually, the fuel runs out, the quasar dims, and the heated gas cools over hundreds of millions of years before forming the next generation of stars. That future state represents what astronomers call a red and dead galaxy. Massive, elliptical, containing old stellar populations with little ongoing star formation. Our observations suggest most massive ellipticals in the nearby universe went through quasar phases billions of years ago. TON 618 provides a window into that earlier epoch, showing us what these systems looked like during their violent youth. The jets deserve emphasis. Streams of plasma accelerated to 99.9% light speed, carrying power equivalent to 1 trillion suns, extending across hundreds of thousands of light years. These aren't side effects. They're integral to how supermassive black holes influence their environments. The jets inject energy throughout the circumgalactic medium, heating gas and maintaining it at temperatures too high for star formation. They shape the distribution of gas on scales far larger than the accretion disk, or even the host galaxy itself. Magnetic fields thread through the entire system, though we can't observe them directly. Theory predicts strong fields near the event horizon, where they extract rotational energy from the spinning black hole and channel it into the jets. Fields in the accretion disk affect how matter spirals inward. Fields in the nebula might influence gas dynamics and future star formation. Understanding these fields requires polarization measurements and radio observations that push current instruments to their limits. The host galaxy remains essentially invisible, outshone by the central quasar despite potentially containing hundreds of billions of stars. We can infer its properties from the black hole galaxy mass relationship observed in nearby systems, but we can't observe it directly. Future telescopes like JWST or the Extremely Large Telescope might eventually resolve details, but for now, the galaxy is lost in the glare of the accretion disk's brilliance. This creates an odd situation where we know more about the black hole, an object we can't see directly, than about the galaxy surrounding it, which should be far easier to observe. The black hole's mass comes from measuring velocities of orbiting gas in the Broad Line region. The galaxy's stellar population remains hidden, revealed only through gravitational effects and statistical relationships with other systems. Discovery histories often reveal something about scientific progress. TON 618 was photographed in 1957, catalogued as a mysterious violet object, then sat in records for 13 years before anyone realized what it was. Only after quasars were recognized as a distinct class of objects in 1963, and after radio observations flagged it as unusual in 1970, did spectroscopy reveal its true nature. We observed it decades before understanding it. This pattern repeats throughout astronomy. We detect signals, catalogue objects, take images, and only later, sometimes much later, do we grasp their significance. The delay reflects both technological limitations and conceptual ones. Sometimes we lack instruments sensitive enough to observe crucial details. Sometimes we lack the theoretical framework to interpret what we're seeing. Progress requires both better observations and better theories, each informing the other. For TON 618, key questions remain unanswered. We don't know its precise three-dimensional structure. Observations provide projections on the sky, but not depth information. We don't know the detailed velocity field throughout the nebula. We don't know how magnetic fields vary spatially. We don't know the metallicity distribution in different regions. We don't know whether previous active phases occurred before the one we observe. Future observations will address some of these gaps. JWST can probe dusty regions invisible at optical wavelengths. The extremely large telescope will resolve structures 10 times smaller than current observations achieve. The Square Kilometre Array will map molecular gas and magnetic fields with unprecedented detail. Gravitational wave detectors might eventually sense mergers involving similarly massive black holes, revealing formation pathways and growth histories. But some questions may remain permanently unanswerable. We observe TON 618 as it was 10.8 billion years ago. The light we see has been traveling since the universe was only 3 billion years old. We have no information about what's happened since then. The system has evolved for 10.8 billion years in ways we can't observe. The quasar might still be active, or it might have shut down billions of years ago. The nebula might have formed stars, or it might remain diffuse. We simply don't know. This limitation applies to all high redshift observations. We see distant objects as they were long ago, frozen in time at whatever epoch their light departed. The universe has continued evolving, but that evolution remains hidden from us, blocked by the finite speed of light. Only by observing many similar systems at different redshifts can we reconstruct the evolutionary sequence, piecing together cosmic history from snapshots at different epochs. TON 618 occupies a crucial position in that sequence. It formed during the peak of quasar activity, when black hole growth rates and star formation rates both reached their cosmic maxima. Understanding this epoch reveals how galaxies transitioned from gas-rich, actively forming systems to gas-poor, passive ones. It shows us when and how feedback mechanisms became effective at regulating growth. It constrains models of cosmic evolution that predict the properties of galaxies we observe today. The broader implications extend beyond individual objects. Ultramassive black holes like TON 618 provide tests of fundamental physics in extreme conditions. General relativity predicts how spacetime should curve near such massive objects. But we've never tested those predictions in regimes this extreme. The event horizon should behave in specific ways. Tidal forces should follow predictable patterns. Time dilation should match theoretical calculations. Confirming these predictions validates our understanding of gravity where it matters most. Quantum effects remain mysterious. Hawking radiation suggests black holes emit thermal radiation and eventually evaporate, but the timescale for TON 618 exceeds 10 to the power of 100 years, so long that the concept of time itself becomes questionable. The information paradox asks what happens to information that falls into a black hole, and no consensus answer exists despite decades of theoretical work. TON 618 embodies this paradox as dramatically as any object can. String theory and quantum gravity approaches proposed solutions, but experimental tests remain impossible with current technology. We can't probe physics at the Planck scale where quantum effects should modify general relativity. We can't observe the interior of event horizons where singularities supposedly lurk. We're left with mathematics and theoretical arguments, unable to test predictions directly. TON 618 reminds us that the universe contains regimes where our best theories break down, and new physics must eventually emerge. The scale still doesn't quite register. You can recite the numbers: 1,300 astronomical units Schwarzschild radius, 66 billion solar masses, 140 trillion times solar luminosity. You can follow the comparisons: 40 times Neptune's orbit, more massive than the Milky Way's stars combined. Light takes weeks to cross its shadow. But actually visualizing it, actually grasping what those numbers mean in any visceral sense, that remains beyond human capability. Your brain compresses the information into abstractions. TON 618 becomes a category, ultramassive black hole, rather than a thing you can imagine. The nebula becomes a number, 100 billion solar masses, rather than a physical structure you can picture. The jets become a concept, relativistic outflows, rather than actual streams of plasma you can visualize. The translation from measurement to understanding hits fundamental cognitive limits. This limitation isn't failure, it's recognition of scope. The universe operates at scales both far smaller and far larger than human experience spans. Quarks and electrons inhabit realms trillions of times smaller than anything you can see. Galaxy superclusters and cosmic voids extend billions of light years beyond anything you can travel to. Your intuitions, shaped by evolution to navigate a world of medium-sized objects moving at moderate speeds, simply weren't designed for extremes in either direction. What you can grasp is relationship and context. TON 618 isn't just large, it's among the largest black holes known. It isn't just distant, it's one of the most distant quasars we've studied in detail. It isn't just massive, it's at or near the theoretical maximum mass achievable through accretion. These relationships place it in context, showing where it fits in the cosmic hierarchy of extreme objects. You can also grasp implication. TON 618's existence tells us something about the early universe, that conditions allowed such massive black holes to form within 3 billion years. Its properties constrain theoretical models of black hole growth and galaxy evolution. Its feedback effects demonstrate how black holes influence their environments on scales far exceeding their physical size. These implications connect TON 618 to broader questions about cosmic structure and evolution. The human tendency to seek meaning in observations runs deep. You look at TON 618 and want to know what it means, what significance it holds beyond just being large and distant. The scientific answer focuses on what we learn, constraints on accretion physics, tests of general relativity, insights into galaxy formation. But there's another meaning, less precise, but perhaps more profound. TON 618 represents the universe's capacity for extremes. Physics allows black holes to exist. The laws of nature permit matter to collapse into regions so dense that space-time itself warps beyond recognition. The same forces that shape ordinary stars and planets, scaled up and concentrated, produce objects that challenge our ability to understand. The universe isn't obligated to operate at scales we find comfortable or comprehensible. It simply operates according to its laws, producing whatever those laws allow. This indifference to human comprehension is itself significant. The universe doesn't care whether we understand it. TON 618 existed long before humans evolved, will continue existing long after our species is gone, and would remain exactly as it is, even if no conscious observers ever studied it. Our attempts to measure and understand it reflect our curiosity, not any intrinsic meaning the object possesses. Yet that curiosity matters. Humans are the universe's way of studying itself, matter arranged in such a way that it can contemplate its own existence and origins. When you think about TON 618, when you grapple with its scale and try to understand its properties, you're participating in something remarkable. Atoms forged in ancient stars, now arranged into a human brain, considering the nature of an ultramassive black hole billions of light years away. The universe examining itself through the medium of consciousness. That's the real story TON 618 tells. Not just facts about mass and size and luminosity, though those are important. Not just implications for cosmology and galaxy evolution, though those matter too. The deeper story is about the relationship between the universe and the minds that try to understand it. How we push against the limits of comprehension, developing mathematics and observations and theories to grasp phenomena that exceed our intuitive capabilities. The effort itself is valuable, regardless of how complete our understanding becomes. We'll never stand on a planet orbiting TON 618, never directly observe its event horizon, never witness its eventual fate billions of years from now. But we can measure its properties, model its evolution, connect it to theoretical frameworks that explain how such objects form and grow. We can place it in context, understand its significance, and use it to test our theories about the cosmos. That's what science offers, not complete understanding, but progressive refinement of incomplete understanding. Each observation adds detail, each measurement constrains theories, each new instrument reveals previously hidden aspects. The process continues, building knowledge incrementally, occasionally making dramatic leaps when new technologies or insights become available. TON 618 will continue revealing secrets as our capabilities improve. JWST observations might resolve the host galaxy's structure. Gravitational wave detectors might sense mergers involving similar objects. Advanced simulations might explain how it grew so massive so quickly. Future generations of astronomers will study it with instruments we haven't yet imagined, asking questions we haven't yet formulated. For now, you know what can be known from current observations. You understand the scale even if you can't truly visualize it. You grasp the implications even if the full picture remains incomplete. You've confronted one of the most extreme objects in the universe and emerged with some measure of understanding, however limited human comprehension must be when faced with phenomena this far beyond everyday experience. The universe contains TON 618 and countless other wonders, objects and phenomena that push the boundaries of what physics allows. Some we've discovered, many more await detection. Each one challenges us to expand our understanding, to develop new ways of thinking about matter, energy, space, and time. Each one reminds us that reality is richer and stranger than we might imagine. That's how big TON 618 really is. Not just in astronomical units or solar masses, but in the space it occupies in our attempts to understand the cosmos, a landmark at the edge of comprehension, pointing toward mysteries that still await resolution.